in the front. Okay, we don't have enough Malaysians in here for anyone to get the jokes, unfortunately. But this talk is going to be, like, I had to do a last-minute change. I was going to do this whole thing on anti-forensics, but none of my code actually works. And so what I decided to do was to do what I know best. So this is going to be called Panduan Mencari Gadis Malam by Papa Ayam. All right, there's 3 people laughing. For everyone else, it means the guide to finding women of the night. Pengantar. Okay. Gadis malam. Di mana? Umur berapa? Berapa? Terlampau mahal. Okay. So, for everyone else that just said where, how old, how much, incredibly expensive. So, onto the actual presentation. It's called How the Leopard Hides His Spots, because I assumed everyone here from Malaysia is familiar with, classical colonial literature by Rudyard Kipling, right? Okay, so the idea is that this is a talk on anti-forensics specifically for the OS X platform. As it happened, I spent quite a lot of time working on application-level file format attacks. So a lot of this is actually cross-platform. Like, we'll spend some time looking at HFS-specific attacks, but also things we can do against, for example, SQLite. Briefly, an introduction of myself. My name is The Grugq. I've been an anti-forensics researcher since 1999, which basically makes me the longest-running anti-forensics researcher in a field of about 2 people. I'm number 1. I basically work as an independent security researcher, which is the nice term for hacker, and I live in Thailand, so I'm quite close to here. So I'm not jet-lagged, unlike everyone else, which is awesome. A lot of people ask me why I do anti-forensics. Actually, the specific example I have for this is when I gave an earlier version of this talk, my old one on Unix, to a police conference. I had this very, very big, like 2-meter tall, shaved head guy with his name on his knuckles come up and say, like, I've got one question. I'm like, yes. He goes, why are you doing this? Police don't like it when you make their job difficult. They really hate it. And the problem, as I see it, is that forensics is actually an integral part of the information security lifecycle, right? From penetration testing, intrusion prevention, intrusion detection, incident response, forensics, it's all part of the security lifecycle. And as a result, it should be exposed to the same sorts of research as other parts of the security lifecycle, such as finding bugs in other pieces of software. So unless someone's doing this, then forensics is never actually going to catch up, and it's going to continue to remain vulnerable and insecure. The other thing is that it's still very much greenfield research. Like, if you're looking at doing buffer overflows on Windows, you may as well just spend your time reading everyone else's papers and following in their footsteps, because it's going to be really hard to do something new. But if you're doing anti-forensics, you basically just pick a platform, and anything you do is the first stuff that's ever been done on it. It's really easy. It's great. It's like kicking someone when they're down. Okay, so now, to get everyone on the same page, you get a 1-slide introduction to digital forensic analysis. Okay? The first thing to know is that forensics only exists within the context of an investigation. So anything that's like done to just look around doesn't count as forensics, right? Forensics only exists within the context of an investigation. You're responding to an incident. You're investigating that incident and then drawing some sort of conclusion. There's only about 3 things you need to do. You need to preserve the data in the original state. You need to extract all the evidentiary data possible from that snapshot of the original state, and then you need to present the evidence, right? Piece of piss. We're going to be looking at all of the things that happen at step 2, where you extract the evidentiary data from the snapshot. So let's look at that as anti-forensics. Anti-forensics gets a 2-slide introduction because it's a lot more complicated. Slide number 1, data is evidence, right? Everything that you can possibly do on a system leave some sort of trace behind, right? Everything that you do in some way creates data that needs to be removed or hidden, right? So your goal when doing anti-forensics is to reduce the quantity and quality of evidentiary data. And there's several different ways of doing that. So there's basically 3 types of strategy that you can employ. First off, we have data destruction, right? They can't find what isn't there. So if you destroy the data, there's nothing to be recovered and used against you in a court of law. What this comes down to is basically removing evidentiary data ex post facto, which means after the fact. I looked it up on Google. So the idea is that after you've done something that you're not very proud of, you get rid of the evidence completely by destroying absolutely everything. It's very difficult to do this in a subtle way. Like, it's very difficult to only remove part of a file system. Part of the reason for that is modern systems scatter data absolutely everywhere, right? When you download a file, there's like a cache. It might update the registry on a Windows machine. It'll be written to disk in multiple different locations. That will create directory entries. That will update inode times. Like, all sorts of things happen all over the place. And finding and tracking down each of these instances and reverting them to a state prior to the bad thing, that's actually incredibly difficult to do. So generally speaking, the scorched earth policy is the way to go. What that means is just fucking burn it all, right? Don't try and get rid of like only the dirty pictures you downloaded. Just destroy the hard disk. Get a hammer out, go at it. That's the way to do it. You're like really doing proper data destruction is very difficult. Fortunately, in the real world, you don't actually have to do proper data destruction. You just need to do like just enough to make a forensics investigation difficult. So you don't need to destroy all evidence. You just need to make the evidence useless in a court of law. So demonstrating that it's been modified is generally sufficient. But like, we're hackers, so we're far cooler than that. So no data destruction for us, right? So that's strategy 1. Strategy 2, data hiding, right? If they can't see it, they can't find it. So we're going to stick our stuff somewhere they can't see it, where the sun don't shine. The idea is to store data outside of the scope of the investigator's tools. So if your data is stored beyond their visibility range, it's secure. The problem is it's only secure for a short period of time. Like, basically, you're dealing with bug death. So when you're exploiting a bug, you don't have an infinite period of time before that bug dies. It's just like everything else on the internet. The good thing is forensics is a very, very slow-moving field. So when I first did a release of a bug back in like 2002, there was the RuneFS, which basically just used the bad blocks file. It took the sleuth kit 9 months to fix what was essentially a 1-line patch, right? So bug death is a very, very slow process. You don't really need to worry about it that much. It's not like hours like on the internet. It's, possibly years. But anyway, so yeah, because you need to worry about bug death, don't forget to encrypt, right? So there we go. Data destruction, data hiding. Next one, data contraception. They can't find what was never there in the first place, right? So the trick with this is you never touch the disk, right? The idea is if you don't create evidentiary data, you don't have to remove it and you don't have to hide it. So you stay in RAM. You avoid accessing things that will lead back to you. You avoid using tools which are custom made. You use tools which are generic so that it's very hard to create a profile. So it's very hard to trace you down to a specific individual. The problem with this is it's a real pain in the ass to do, particularly if you're drunk. So like, you really have to plan and be prepared. You can't just go out and like just start hacking whatever you feel like. You have to like, okay, today I'm going to be going after this. Like, here's the plan. You script everything out beforehand. You get your tools ready, and then you execute. And most people don't really do that. I wrote a tool to make it a lot easier by allowing you to script interactions with the command line. That tool is called Hash. You can download it from tacvoip.com. But generally speaking, like doing proper data contraception is very annoying, right? So those are the 3 strategies that you can employ. Now we're going to be looking at tactics, ways that we can actually implement them. We're only actually going to be looking at data hiding attacks because they're far sexier than the other ones. Like, data destruction is easy, you just destroy everything. Data contraception is hard and annoying, and I did it last year. And so let's do something that like involves like reading source code and finding bugs and writing code. So when we're looking at a good data hiding attack, there's only really 2 things we need to worry about. First of all, it has to be hidden, right? If it's not hidden, it's not a data hiding attack. You'd be surprised how much this foils people. I remember working with a guy who told me that his clever technique for hiding systems on Unix was to put a dot in front of the name. It actually worked. That's the sad thing. But like when we do pen tests and we find rootkits, we find that they usually don't even bother with the dot. They just pick a home directory for someone who hasn't logged in for a year and stuff all their stuff in there. No one cares. Right? So we're not that blatant. We want to do something clever. We're going to go for a hidden attack. The other thing is we want it to be robust, which means that when we put our data in there, when we come back to pull it out, it shouldn't have changed and be destroyed or gone lost. Right? So we don't want our data to vanish. If we wanted our data to vanish, we would use a data destruction attack. Right? So what we're going to be looking at specifically is ways of exploiting structured storage bugs. Structured storage is pretty fundamental to computers. Everyone's intimately familiar with all sorts of structured storage approaches. Yes? I can just skip the next section. Okay, what the hell? There's one person in the audience who says I should go for it. Okay, so the first sort of structured storage we're going to look at is file systems. File systems are basically a way of pairing user data with names. That's all they do. The way that they implement it is a bit more complicated. So the idea is that you take a discrete stream of data and you associate a human-readable name with it. And then you can create a path with a number of these names and you get to that specific piece of data. Right? That's all it does. The way that it implements it on disk is what we're going to be spending most of our time looking at. There's two types of data within the file system. There's data which we completely ignore because data belongs to the user and it changes all the time. And then there's metadata. Metadata is used to organize the file system, right? To organize the internal structure of that structured storage medium. And that's what we're going to be looking at. So file systems, this is another one. File systems basically provide an operating system level of CRUD, which is create, read, update, delete. Obviously, right? I'll take that blank stare as a yes. Okay. Files have basically 4 critical components. All sorts of files use different names for them, but the file systems basically break down into only 4 types of object, right? There's a header, which basically tells you the global layout and properties of that file system. That has to be at a fixed location so you can find it. Anything else can be created dynamically, but you have to be able to find the header, right? Then you have a block. A block is just a discrete chunk of data. It's going to be the lowest atomic addressable component of that file system, right? Then you have a node. A node is a collection of metadata for a single file plus one or more block streams. So a block stream is basically an ordered series of blocks containing data, right? So you've got your block list, you've got your node, and then you have a map. So what a map does is it takes a name and it pairs it with a node, right? So to make this concrete, I'll give everyone examples from NTFS because you are all intimately familiar with the internal structure of the NTFS file system, right? Once again, the blank stare of affirmation. Okay, so the header on an NTFS system is called the boot block for historical reasons. A block is called a cluster. There's usually 4 letters that comes afterwards, but I'll leave those out because there's ladies in the audience. So basically, a cluster is the idea is that there are multiple sectors put together as a cluster of sectors. It makes it easier to read large portions of data off the disk. There's some other stuff to go into. A node is actually an entry within what's called the master file table. The master file table is itself a file that has entries for itself. And then there's maps, which would be directory files, as you know them, but they're actually also entries within the master file table, which makes it a lot clearer, I can see, right? Yes. Okay, this one might work a bit better. FAT, right? Everyone's familiar with the FAT file system. It's used on all your mobile phones, right? It's everywhere. The file system that will not die. It's older than I am. It's from like the early 70s. It's a fucking abomination, similar to myself. But the idea is that there's this boot block which describes the entire file system, and that's the first sector of the disk. A block is once again called a cluster. A node is a directory entry. So inside a directory file, there's actually additional metadata associated with that file name. And then there's a FAT chain, which is within the FAT table itself. There's a chain of blocks, which creates the block list for user data. And then finally, your map is itself a directory file, right? So now everyone is very, very comfortable with the idea of a directory, block, node, map. I've given you like a couple of examples that you're all drawing on your vast resources of low-level disk hacking. Okay, never mind. So let's just talk about like how does one go about doing a data hiding attack against structured storage? It's very simple. Basically, you need to allocate space where you're going to put your data. The ways to do that is basically to exploit bugs in the code that interprets and uses that structured data. Right? There's roughly 3 types of bugs that we're going after. There's bugs in parsing, so it might incorrectly read the structured data. There's bugs in interpretation, so it might incorrectly interpret the structured data on the disk. And also there are bugs in presentation. So when it takes that data and presents it to the user in a forensics tool, it might inaccurately show the contents of what they're looking at. Right? So once you've allocated that space, you need to inject data into that. How do you do that? Very simple. Fisting. Fisting is the file system insertion and subversion technique. Right? It's a very generic technique for exploiting structured data storage. Basically, all you need to do to fist is you find a hole and you fist it. So right now you're probably thinking, what holes can I fist? Well, first you need to find a fist-sized hole. Generally speaking, these things that you're looking for are special files within a file system. So they're files that have implicit readings that are dealt with implicitly rather than explicitly. You look for slack space. Usually there's ways to allocate slack space or to gain additional slack space within metadata structures. And the best part is slack space is inaccessible from user land, and it's actually frequently inaccessible from forensics tools as well. And then finally we have reserved portions of metadata structure. And the thing to remember is reserved means reserved for hacker use only. So anytime you see reserved in a metadata structure, you can put your data there. Go ahead and fist it. No one's going to notice. OK, so forensics tool bugs that we care about are, generally speaking, they're related to incomplete or ignorant implementations. So the guys who put together the file system parsing code for forensics tools are, generally speaking, idiots. They don't read the specs properly, and then they implement just enough to access the specified data. They don't go the next step, so that's what we need to do. So there's usually underused or non-typical or atypical usages of structured storage features that they ignore. There's also logic bugs, so there's ways that you can access edge cases in certain types of structured storage, and you can exploit those edge cases for data storage. And finally, there's straightforward security bugs, like buffer overflows, integer wraps, that sort of stuff. Generally speaking, I don't recommend going for a security bug because it's very difficult to anticipate ahead of time what sort of forensics tool is going to be used against the disk image. So if you go out of your way to put like a really clever encase attack in there and the guy uses sleuthkit and FTK, then you're screwed. Right? So you're better off just playing it subtle. So aspire to subtlety. Avoid like making waves and upsetting people. So fisting for all. The great thing is you can basically fist any structured data storage at all. Right? We're going to look first of all at fisting file systems, and then we're going to look at application file formats. Okay, so now specifically just to look at OS X, we're going to look at HFS+, and then I also have the application file format attacks that kind of come under OS X here, but you can use them on anything. So I'm now going to give everyone a lightning quick introduction to HFS, the HFS+ file system. So here's your induction. HFS stands for the Hierarchical File System Plus. It came out with OS X. There's some backwards compatibility stuff in there for OS 9 and earlier. It was very, very heavily influenced by HFS, which is just the hierarchical file system, no plus. The on-disk structure is actually quite complicated because they use B-star trees. And B-star trees are a specific form of binary tree that, like, when it gets written out to disk, it is a little bit annoying to deal with. If anyone's really interested in the technical specifications for this, the Apple Technical Note 1150 is actually very, very good, and I highly recommend it. It makes great reading. You can, take it on the train, have a nice cup of coffee. Yeah, maybe it's just me, but they really write it quite well. So this is what the file system looks like. It's mostly gray and white with some black bits. Okay, so you can kind of see at the top there, there's the header, then there's several special files, then there's allocation space, there's a copy of the header at the end, and that's pretty much it, right? So the components that I mentioned earlier, we have the header. So in this case, the header is called the volume header. A block is called a block, and a node is actually, it's made up of different parts. So the block lists are made up of extents, which can be stored in a couple of different places. And the metadata is stored in several different catalog file entries. So the catalog file basically contains your file system structure, the whole directory structure that you're familiar with, right? And then the maps itself are the catalog file entries. So there's sort of two core concepts that you need to get your head around. First of all, there's data forks, and the other one is B-star trees. So data forks are pretty straightforward. Basically, a data fork just is a stream of data that's stored in a specific location. So what you have is the location information that says start here and read this number of bytes. And it's got a series of those records. And then it's also got the overall size and of the user data contained within that. So what we're looking at is this, right? So your fork data is basically this header at the top, which has a logical size. So that's the size of the internal data. There's the total block. So that's the total number of blocks that have been allocated to store all the data. And then there's an array of these descriptors, which basically tell you the first block and then the number of blocks to read. One of the areas that you should not store data is between the end of the logical size and the end of the allocated blocks. That's what's traditionally called slack space. Every forensics investigator knows how to find data there. And basically, that's the only place that they know how to look, right? So if you tell them that you're using slack space, this is where they're going to go. They're going to look at all of the blocks that have been allocated. Then they're going to find the end of your user data and that space at the end. They're going to look at that and be really excited if they find something. So don't put your shit there like the the anti-forensics toolkit inside Metasploit. That's where it puts all of its data. Don't do that, it's stupid. Okay. There are a number of special files within the HFS Plus file system. There's the allocation file. So the allocation file, basically, it stores a bitmap to indicate which blocks within the file system have been allocated or not. There's the catalog file, which stores information on basically all the metadata about a file specifically itself. There's the extent file, which stores fragmented file block information. There's the startup file, which is optional. It's used on very, very old archaic systems, and it tells you where to find the kernel loader on a file system. And then there's the attributes file, which stores extended attribute information. All right? We'll come back to all of these when we start attacking them. Okay, so B-star trees are used very, very heavily within the HFS Plus file system. Basically, what a B-star tree does is it's a binary tree where all of the leaf nodes are connected in a linked list. The idea is that a file is divided up into nodes. Each node has an address. You can point to it by indicating the address. It's pretty straightforward stuff. Nodes are basically one of 4 different types. You have header nodes, which store metadata about the entire B-star tree. You have map nodes, which tell you about the allocation. They have a bitmap indicating the allocation of nodes within that file. You have index nodes, which are basically a pairing of a key and a node pointer so that you can rapidly do your binary tree stuff. Everyone's very comfortable with binary trees, right? While start is less than end, for mid equals, blah, 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 all that. Yeah, of course. I won't go into it. So, and then finally you have your leaf nodes, which store a key and a data record. So once again, I have a very cool illustration, which I did not copy directly out of the technical docs. So this is what a node actually looks like, all right? This is kind of important. The key thing to look at over there is the part where it says free space. Right? You can cross that out and write in reserved for hacker usage only. So the idea with a B-star tree node here is that you've got a number of records inside of there, And any unallocated space that isn't being occupied by a record is available as free space that can be used later on. For everyone that wants to see what a B tree looks like, it looks like this. It's got a red bit, an orange bit, and some other colors. Basically, at the top, what you have is the header node, which has a pointer to the first leaf node and the last leaf node. The ones in the middle are index nodes. So you would follow down through these index nodes to get to your actual data in the leaf nodes, and the ones at the very bottom are leaf nodes containing the keys and the actual data, right? So you'd follow your tree down with, like if my key is less than 8, then go to the left, otherwise go to the right, sort of thing. Yep. Okay, so let's break that. Okay, so we're going to look at like specific attacks that we can do against HFS+, right? Starting out with just file allocation attacks. So as I mentioned, there are special files. You can do cool things with special files. So one of them is there's a special file called the bad blocks file. The bad blocks file exists to allocate blocks which contain bad sectors and prevent them from being used by user data. So you go to the extents file and you mark extents that hold bad blocks as belonging to the file number 5. CNID is catalog node ID. So any extent that's owed by catalog node ID 5 is not flagged by the file system checker, and it's basically ignored by forensics tools because, once again, the old like bad blocks trick, it's the oldest one in the book, and it still works, particularly on HFS+. But this is like way too lame for us. Like, it's very, very obvious. We're not going to do it. So there's also, as I mentioned, there's the startup file. Once again, the startup file is used on very, very archaic systems. The idea is that if you have a bootloader and it needs to load the kernel, you don't want to have to go and write the entire HFS+ file system into that bootloader. So you load the kernel, you put it in like a specific location, and you write your bootloader to be able to read just this one file and then to be able to go there itself. It makes it a lot easier. No one actually uses this because it's fucking ancient. So what you have instead is a zero-length startup file which is ignored by everything. What can you do? Well, it doesn't have to be zero-length. It can be an arbitrary size. So you simply take the startup file, you allocate space for it, and you put your data in there. Done. Similarly, you can do this with the allocation file, in which the allocation file has space that's been allocated for the bitmap, and the kernel will not actually look beyond the last element of that bitmap. But there's nothing that tests that the size of the allocation file is exactly the right size to store that bitmap. So you can increase the size of the allocation file and put your data at the end there. I mentioned that there was some backwards compatibility. One of the things that happens is older Mac OS 9 systems wouldn't be able to access an HFS+ drive. So what they did is they put the HFS+ drive inside an HFS file system. It's called an HFS wrapper. So you can actually have your HFS file system embedded inside an HFS file system, right? Got that? HFS file system inside HFS+. Everyone looks at the HFS+. But you actually have two file systems that you can do stuff with. So the HFS wrapper you can actually use for data storage yourself. So you can allocate additional space within the HFS wrapper, particularly at the end of the bad blocks file. So the embedded HFS+ volume is marked as bad blocks within HFS, within the outer wrapper. You can extend the size of the bad blocks file and then use the slack space at the end. All right? Very straightforward stuff. This will work probably for the next few years because even if you tell them what's wrong with forensics tools, they don't fix them. Right? It's not like part of their business to fix problems. It's only to like come out with new features and stuff. Okay, so those are attacks that we can do against allocation files. I haven't implemented them yet because it's actually really, really irritating to do allocation with all of the B trees. I've spent most of my time implementing my B tree code. So attacks that we can do against the binary trees themselves. These are much more interesting because an allocation attack, where you basically take a file that should have 0 length and you make it non-zero, is very, very easy to detect, right? If you have a startup file that's not 0 length, maybe there's something in there that's a bit weird and you can look into it. If you have a large number of bad blocks, maybe you want to look at those, right? These are not subtle. This stuff's a bit better. So one of the things that you can do is a B tree has a special type of node called a map node, which once again, it contains a bitmap to indicate which nodes within that B tree have been allocated. There is nothing that says the number of map nodes has to be exactly the right number to hold a bitmap that fits the entire tree. You can extend the number of maps, you can add new map nodes, and use those maps for data storage. Right? So you can add map nodes at the end of the linked list, and they're not going to be accessed by the kernel because they would indicate bits, or basically they would indicate nodes that go beyond the end of the file. So they're outside the scope of that B tree. Nothing to worry about. This is very, very easy to implement, but for some reason my code doesn't work. So this demo gets skipped. No complaints there, right? OK. Next up, there's actually, as I mentioned, there's free space inside nodes. You can actually do data storage inside that free space. Once again, my code doesn't work. So we're going to skip this demo. But what I can show you is how it mostly works up until the point that it gets written to disk, when it stops working. Which, it drove me nuts. I've spent an hour working on it, and it gets all the way, at the very, very lowest layer I have, I can see the buffers that are supposedly getting written to disk, and they contain all the data. And then when I read it back in, the data is gone. So I'm going to lodge a complaint with Apple saying that there's something wrong with their disk driver that erases my data hiding attack before it gets down to the disk. I'm pretty sure that's the only possible explanation at this point. So let's look at something else. We're going to look at how we can use Unicode. There's Unicode bugs that we can exploit, and we can actually do data storage inside Unicode strings. Everyone's very excited by this, I can tell. Yay, UTF-16. All right, you people suck. OK, so what we're going to be looking at is zero-width Unicode glyphs. Basically, a glyph is something that gets displayed to the screen or advances the cursor on the screen. Right? UTF-16 has what are like non-glyph characters. They occupy space within a UTF-16 stream, but they don't display any glyphs when they're printed to the screen, and they don't actually cause the cursor to move. So they're essentially invisible. And we only need two of those. So the first one we have is the null character, which is basically all zeros. And the other one is what we have is the zero width space. It's a space that occupies zero width. Right? Since we've got two, that gives us what? 1 and 0. Right? So now we can do data storage by converting our bytes into chunks of Unicode characters. Right? So we actually now have a way of converting a stream of bytes into a stream of zero-width Unicode characters. How awesome is that? Very awesome. Correct. OK, so the cool thing about this is mostly what happens is UTF-16 gets converted to UTF-8 on the way back. So it will be read up as UTF-16 off the disk, and then it will get converted to UTF-8 to be displayed on a screen. And the awesome thing is the way that the null character over here gets converted into UTF-8 is it becomes a null terminator, which means your null character actually terminates your UTF-8 string, which means all of the rest of the data is now invisible completely, it vanishes in the conversion process itself. Right? So you can actually hide data in a file system by converting your data to invisible UTF-16 characters, appending them to the names of appending them to file names. So you'll have a file name that's 2 characters plus 200 characters of UTF-16 data. When the forensics investigator comes by trying to look at where all this stuff is, he will read up the file name, convert it to UTF-8, which strips out all of your data, and then start looking inside the contents of that file for your data, when his tool has already basically erased the data for you. Right? So it's data that would get printed to the screen. It's incredibly ironic. Yes? The data he's looking for is displayed directly in front of him, but it's invisibly displayed. Wow. Right? So where can we use UTF-16? Well, there's some cool things, like the iPod iTunes database actually uses UTF-16 for everything, right? That means the artist name, the album name, the genre name, the path to the file, basically every single piece of metadata associated with a track inside an iTunes database is stored in UTF-16 characters. And it's duplicated for every single entry. So if you have a track that, like if you've got 13 tracks from the same album, each of them will have the album name individually embedded within that entry. All right? It's also used for file names, for example, in HFS+, in NTFS, and in FAT32, right? In what's called the long file name format. So you can actually do attacks with UTF-16 characters against FAT32 on your phone. Pretty cool stuff, I can tell, right? And obviously, you can do it inside documents. So you can have your document encoded into the UTF-16 character set, and you can do your data storage in there, right? So I call this the ZWU attack, ZWU. We're going to look only at how we can attack an iPod database. Basically, each entry in an iPod database has a maximum of 255 Unicode UTF-16 characters. It takes us 8 characters to encode a single byte, which means that per song, at a maximum, we could encode about 31 bytes. So only looking at like the artist, the album, the track name, and the path, theoretically, we get about 100K of storage per 1,000 tracks in an iPod, which isn't too bad. If you've got a large iPod with a large number of tracks, you can actually have a couple of megs of storage space in there. That's invisibly embedded. There's some downsides with iPods, like I've been working a lot on iPod attacks. There's also attacks against the structured storage format that they use, the MHBD database. You can do things in there. This code actually does work, except I don't know how to make a terminal display over there. So imagine that I'm executing this from the prompt. I can make it show up one character at a time if that helps anyone. You can pretend I'm typing. OK, so I've written a module called UTF-Fool. Basically, it only has 2 methods, to Unicode and from Unicode. As you can see here, if we call to Unicode, what we get back is an 88-character length string, which when we print out is 0 width, right? The problem is if you print it directly without encoding it like this, it gets converted, like all of the 0 width space characters get converted into normal space characters, and then it shows up on the screen. So it looks a bit naff. But honestly, it does work. It's one of my few demos that does work. Please believe me. OK, so like the cool thing is you can attack pretty much anything, including even Unicode. Right? Unicode is itself simply a structured data storage format. Right? So you can fist the Unicode. So next up, we're going to look at how we can move beyond structured format and look at other attacks that we can do. This one's kind of funny because it simply takes a slightly different way of thinking. So we're going to look at browser cookies. Right? First of all, what is a cookie? It's very simple. A cookie is a URL that's been associated with some sort of key, a variable name, and a value. And chances are that value is a base64 encoded chunk of encrypted binary data that's been sent to you by the website. Right? Well, what do we want to store? We want to store a base64 chunk of encrypted binary data. Anyone having an aha moment? Yes? Right, no. OK, so the idea is that you can actually use your cookies file for hidden data storage because you can create fake cookies that contain nothing but your base64 encrypted data. Right? So looking just quickly at the Mozilla's cookie file, it's an SQLite database. You can access it using only the SQLite 3 tool. The schema is very simple. It looks like this. Basically, the only ones that you need to worry about are the name, the value, the host sometimes, and the ID, which should be incremented anyway. So I'll now show you, yet again, another awesome demo on how we can do data storage. This is guaranteed to be ignored by just about any forensics investigator. You create your data storage, you put it in under lolitapictures.com, and you're away. You guys suck as an audience. No, All right, from now on, 2 drink minimum. Okay, so like rather than storing our stuff inside the cookies file, which is a bit lame, oh yeah, one of the other things that you can do, right, I forgot to put this slide in here, but basically you can take the Mozilla cookies file and you can create your own table. And then you can do your data storage directly in that table, right? So you can do create table, my hidden secret data, you know, with a text value, and then put your stuff in there. When a forensics tool comes along, what they're going to do is they're going to open that up, they're going to go to the Moz cookies table and dump all of the data out of the Moz cookies table and then close it, right? They're not going to look at all of the tables that have been defined for that particular database because the people who implement these tools are fucking stupid. So we can do really, really simple things like that, and we're going to get away with it. But let's do something cooler. So what we're going to look at is the SQLite file format. SQLite, once again, structured data storage. All SQLite does is it takes a file, it divides that file up into pages. A page contains a header on the very first page. Then there's all of these free pages, which are not allocated. They're stored in actually it's not a linked list, it's a binary tree, once again. But basically, all of the free pages are stored in a tree, and you can store your data inside those free pages, which we will do. And I actually have a working demo for this one, so like, you guys can relax, calm down, it's all good. Basically, there's more exciting things that you can do inside the page contents. Inside that, it's called a cell, right? Those are what are used to create the binary trees for the tables. Unfortunately, that code is very, very complicated and ugly, so it's not working properly. Unlike all my other much clean code that is also not working properly. But SQLite is really ugly inside. Okay, so SQLite actually, if you have a table in SQLite and it grows very big, SQLite will allocate additional blocks. It will expand the size of that file. If you then drop that table or shrink the size, SQLite doesn't release those blocks back to the system. It keeps the same large size. So what that allows you to do is take an SQLite database, make it very big, drop the table, and then use all of that free space for data storage. All right? So the one problem with that is if auto vacuum is enabled, it can cause your internal databases to be adjusted. And that means when the B trees get rebalanced, all of your stuff gets wiped out. So don't do it on live databases. That's bad. All right, I have a demo. All right, let me see if I can make it work. Oh, uh-oh. Where's my fucking pointer? All right, I can't find the pointer. No demo, I'm sorry. There we go. All right. As you can see, I'm very much prepared for this stuff. Okay. All right, there should be some setting to like mirror stuff, but whatever. Okay, so here's my like really awesome terminal. And what we're going to do is run Python, squeeze, and try and remember the command line options that it takes. Okay, projects, anti-forensics, SQL, Lite, yes. Cookies DB, etc, password. So what this is going to do is erase my etc password file, overwrite a portion of my disk, and crash horribly. Or not. Okay, so in theory now what we have is a cookies.sqlite file, which has my etc password stored inside. And we can probably do strings and see if I've been going to naughty sites. Projects, anti-forensics, SQLite, cookies. Oh, that doesn't look right. All right, there's all of that stuff. You know what? I just remembered, I'm an idiot. Okay, so what happened is, rather than modifying the existing database, I create a new database called test.sqlite, which you can see here. And it's just being created now, honestly. Here's one I prepared earlier. If we run SQLEs, come on, with just this as the input, it will print out the contents. All right, so rm, run it from scratch. All right. Aren't you guys like really glad that I skipped all the other demos? Like you would have got to see this multiple times. All right, so there you go. Pretty riveting stuff, I can tell, huh? All right. So basically what that attack is doing is it is injecting data into the free space within the SQLite file. Anyone doing forensic analysis on SQLite is going to have a significant disadvantage in this case because there are no forensics tools for SQLite, right? Which basically brings us to the conclusion, the future of anti-forensics is out of the file system into the files, right? File systems are known. There's only a few different implementations that you can go after, and it's possible for people to figure out the bugs and fix them. File formats, on the other hand, are pretty much a mystery. Right? You can take an existing closed source application on Windows, reverse engineer the file format that it uses for storage, do your attack against that, and it will never be found ever. Right? Basically, attacking file systems is old hat these days. It's not the place to go after anymore. You want to move into the application space. Once you're at the application space, it's a lot easier to do data storage. So my recommendation is to go for the stuff that I'm working on right now, such as to use the iPod database as a data storage mechanism. One of the reasons that that is a really cool way of doing it is that it's very, very easy to erase because when you plug your iPod into an iTunes computer, it will rewrite the database from scratch and erase all of the work that you've spent 3 nights fucking working on and didn't know that it automatically erases it as soon as it gets plugged in, right? Which is a great feature for data destruction because you can sit there, you see the cops coming, you plug your iPod in, bang, data gone. God damn it. So essentially, the idea that I'm suggesting to everyone is from these days on, you should really focus on data contraception attacks. So how you can stay in RAM longer, the less things that you can do to actually interact with the computer, the better. And also move into the application space. Go after file formats. They're much, much more exciting than going after file systems. Right. Questions? Yo.
How many kernel panics did you trigger on OS X while you were messing around with HTTP+?
I didn't trigger any. Yeah, I didn't do it on my main disk because I'm not that dumb. I learned this one when I used to do all my stuff on Linux. I only had to rewrite my source code twice from scratch. So, but no, like the thing is, file system code is actually very, very poorly written because the assumption is always made that the only person who's writing to the file system is the kernel. And since you're writing the code for the kernel, you can assume that anything that you read back is something that you wrote, right? So they don't do a lot of error checking. I think they got hammered heavily with this like a year or two ago when there was that like all the month of fucking Wangfest stuff. Yeah. But basically, like the HFS plus code isn't that bad. Like it's kind of elegant. Most of the attacks that I've been doing, like I don't fuck up pointers that badly. Like I just like I have right now that I write stuff out, something flushes over it, and my data vanishes in between, and it's very frustrating. But yeah. Any other questions? Nope. So there's no.
I'm just curious about the application of these kinds of attacks. So let's say you were dealing with illegal pornography or something, using a technique like this to
no comment. Like a bit.
But like, what would your interface be? Because putting the data in, you need to pull it out, right? If you're
Yes, see, like there's bootstrapping, there's significant bootstrapping problems, right? So you need to have a tool that allows you to access your hidden data store. But that tool cannot be hidden itself, otherwise you can't access your hidden data store. And if that tool isn't hidden, then it's basically like leaving the keys out next to the safe, right? Like no one can get in unless they know to look underneath the flower pot next to the front door, that sort of thing. So there are problems with that. Most of the anti-forensics, as I understand it, is useful primarily as a post break-in. So you break into a box, and then you need to clean up to make sure that there is less evidence that can be used against you or used to track you down. Like that interests me a lot more than hiding pornography, for example. The other thing is that like most of the anti-forensic stuff here, it's like it's not worth it because you don't actually need to do any of this to hide your stuff from a forensics investigator, right? The best stuff is, number one, don't get caught, right? If you do get caught, wait until you go to like basically try and get a good lawyer because you're going to need it. Like generally speaking, all of the stuff like the child pornography, they always go for the low-hanging fruit. They go for the easiest guys to find. Hackers, they go for the low-hanging fruit. They go for the young kids who don't know how to clean up after themselves, that haven't developed all of the good habits of like wipe the logs, make sure your rootkit is running, all that stuff. The people that they capture tend to be the low-hanging fruit because it's easier for them to do that. Like there's just various sorts of things that like make anti-forensics as a specific region of study not very useful. Like that putting a dot in front of the file name on Unix, that still works. Like that is a very effective attack. And like it's going to continue to work for a very, very long time because you're, from an anti-forensics perspective, your first objective is to not be detected. So your adversary is not necessarily the forensics investigator. It's the system administrator who has day-to-day interaction with that box. If that system administrator isn't suspicious, then there's not going to be an investigation. And if there's no investigation, there's no forensics officer to come and look at the file system. So don't piss off the sysadmin, and you don't have to worry about hiding all of your stuff properly. But yeah, you're right. It's a pointless waste of time. Thank you for bringing that up, Charles. Are there any other questions? No? All right. Thank you.
Thank you everybody for attending day one of our conference. The Pirate Berries talk will start at